Okay, so just to get, I'm going to take a look at our course schedule. And so you'll see here, in assignment 2 and assignment 3, the abstract data type we're talking about is basically a bag, which just means that all the items get thrown in there. You can have you can have multiple of the same item in there. There's no order to them or anything like that. Then we take a little detour and talk about recursion, and then we talk about the stack abstract data type. Then we talk about the list abstract data type. And then we do some sorting and efficiency. Then we talk about a sorted list abstract data type and a queue abstract data type, tree abstract data type, heap abstract data type, dictionary abstract data type. So basically, we're going to go through all these abstract data types. In many of the cases, he splits it into 2 chapters, which is good, I think. First chapter is studying the abstract data type in the abstract. And then the second chapter is, okay, how do we implement this? So that's why several times you see trees and then tree implementations, right? Queues and then queue implementations. All right, so we're starting with bag. The important thing that when you probably need to make sure you got from chapter 1 is just understanding this ADT bag section, because what we're going to be doing, let me switch. I wish there was a way to switch what I'm sharing instead of new share. Yes, there we go. So I want to go to the book. No, that's not what I wanted. This. Okay, so and so in terms of the abstract data type bag, what we're going to be doing throughout the entire course is, when we study an abstract data type in the text, he's going to give us the interface. So here's a description of the interface using an UML diagram. And then here's the actual code for the abstract data type bag. So what we're going to be doing not every week, but most weeks, is we're going to be writing a class that is inherited from an interface. And so the interface sort of defines what the abstract data type is, right? So for a bag, the operations are get the size, find out if it's empty or not, add something to the bag, remove something from the bag, clear the bag, make it empty, get frequency of a certain item in the bag, return true or false whether the bag contains a particular item, and then this 2-vector function, which is kind of interesting, but not the way that. Well, I'll just tell you this: the reason they have a 2-vector function in here is because they're avoiding using iterators. And so it's the only way that they can make it so that, for example, I can print, like say if I wanted to print all of the items in a bag, how would I do that? Well, the way they're providing is we convert the bag into a vector, and then we know how to print out the contents of the vector without having to resort to iterators. Any questions, any comments about where we're headed here? Okay, hold on to that for a sec. No? Okay.
Yeah, it's not caught up enough on the first reading, right?
Okay, fair enough. All right, so let's see. Well, I was going to say something else, but so the other thing I want to point out that's kind of cool is that all of these abstract data types we're going to be studying have a version in the C++ standard template library, right? So I think you're locked. Shouldn't be locked. There we go. Oh, he had a key. Was that locked?
Yeah.
Oh, I don't know how it got locked.
Leave it open?
It's fine. I'll open it in a sec. But yeah, I don't know what the deal is with
Let's
this.
see, okay.
Let me pause the recording here. All right, so let me just finish my thought about if we go, so my favorite place to go look at stuff like this is c++.com. And if you just click on reference and then click on containers, here's a list of all of the header files. Some of them have more than one container inside. So for example, if I click on Q, it contains queue and priority queue, two different abstract data types. So, and as it turns out, a bag is in the standard template library is called an, wait, let me, unordered set, but it's not actually an unordered set, it's an unordered multi-set. Okay, so the difference between a set and a multi-set is that in a set, you can only have one copy of each item, right? In a multi-set, you can have more than one of each item, right? So a bag is an unordered multi-set, right? There's also an ordered, if you just go to set, it's going to be an ordered set and an ordered multi-set. But what we're talking about with a bag is unordered, right? So I could click on this just to take a look at what's in there. And you know, if I was writing the textbook, I would probably just define the abstract data types exactly the way the standard template library does, so that there would be this correlation, I guess. But they don't do that. They have some differences, but you can see insert, erase, clear was one of the ones in the interface we were looking at a minute ago, or at least I was looking at. Find, size, empty, which is true or false. So a lot of similar operations, right? Maybe some with different names. Okay. All right, so let me go back to the text. Why don't you ask a question about chapter 3?
Yeah. So maybe I just don't understand how a two-vector works, because we barely work with vectors. But with the method two-vector is talking about I think because it's trying to find, let's see. I'll just skip reading the description. It says in the for loop, you've got an item count with I, and it's iterating through I, but then it says bag contents dot pushback items I. What's the pushback for? I'm not sure.
Okay. So you're looking at the implementation in chapter 3?
Yeah, I think it's page 102.
I'll do it the long way, I guess. 2. Okay, so pushback is a function in the vector class. From I think I actually used it in the lesson, but
yeah, it adds to the end.
Right.
Yeah.
So basically, we're declaring a vector named bag contents, and then we're going through each item in the bag and putting that item into our vector.
Yeah, I just wasn't sure. It looked like it was trying to say it's going to put it in an order or at the very end. I'm like, I thought this was just going to be a mix match.
Right. Yeah, the order it doesn't. It does happen to put them in the same order, but it's just pushback is just the most convenient way to put something in the bag. So, or in the vector. So, the fact that it turns out to be in the same order is just a coincidence or whatever. Oh yeah. So, right. Assignment 2 is basically taking this code that implements the bag class and changing it so that it's a set instead. And the only difference between a set and a bag is that the set can only have one of each item.
So that's why the text talks about having to remove the gaps because a set can't have gaps, right? Or is the lower array can have gaps?
Well, it's usually a bad idea to leave gaps in your array, period, right? That's more of just a fundamental thing. Yeah, I don't think that's related to the.
It's going to throw off at least 3 things that said like counts and
right. But I think that's true for bags and sets both, or anything else that's using an array. So basically, there's really not that much to do for part 1 of the assignment, which is converting the bag to a set. You know, one of the things you have to do is just go through and everywhere you see the word bag, change it to set, right? And then I think the only other difference is that you're going to have to edit the add function so that it first checks to see if the thing's already in there and doesn't add it if it's already in there, right? Let me take a look at the, assignment for a second. So the other thing is you won't have a frequency of member function. We're going to get rid of that, right? So you're going to start with the bag interface abstract class, and then you're going to change that so that it's a set interface class. And so you're going to change bag to set, and the frequency of member function will be removed. Okay. So then you'll have your interface, and then you'll write your array set class, deriving that from the interface that you just created. That makes sense? Okay. Not too much going on there, I don't think. So the interesting part is part 2, which is where you're going to write set union, set intersection, and set difference. When I was back in the day when I took algebra, this is stuff we studied in algebra 1. But I don't know. Have you guys studied sets and intersection and union in any class?
Yeah, in Math 25, the first chapter.
Okay. How many people have never studied union or intersection? Everyone knows what that is?
You gotta briefly touch on the last class.
Okay. Okay. So just real quickly, and this is explained in the text too, but so union just means take all of the elements from both. You'll have to be careful because you still can't repeat items, right? So if the same item appears in both sets, you only add it once. And then intersection is just all of the items that exist in both sets. And then difference is just start with the left set and remove any items from that set that exist in the right set. That makes sense? Okay. I just realized I'm not really paying very much attention to stuff in Zoom. But I think if someone puts something in the chat, I'll get notified. So, anything else that's on your mind about chapter 3 or assignment 2? So basically, there's not much new here either, right? This is for 99% of this is just a review of arrays. Not even dynamic arrays, right? We're just using regular old-fashioned simple arrays. The only difference is we're just doing it in the context of writing an abstract data type, right? But as far as the coding goes, it's just arrays.
So with 2.2, you're going to be working with two different vector sets, two different arrays. Two different sets. No vectors, right? You could say two different arrays, but I try to be careful about that because that's now we're talking about the implementation of the set, right? As opposed to the abstract set. So it's probably better to describe it as dealing with two different sets. Because then in chapter 4, what we're going to do is the same exact thing again, except we're going to implement it using linked lists instead of using an array. So, but it's still going to be, set union is still dealing with two sets, whether they're implemented with arrays or with linked lists. I just had an aha moment because I remember reading a little bit about linked lists, and it's like you can fill whatever whenever and just send it to the list, and it doesn't have to be in any kind of like pre-designed format. If you just tie things together on the fly, that's kind of cool. Right.
So with a linked list, the memory locations don't have to be contiguous. They don't have to be even in the same order. So yeah, we'll talk about that. Anything else we want to talk about on assignment 2?
Question just about vectors in general.
Okay.
So the arrays, you declare an array, you have to delete that later on, or like you have to free up the memory later.
With a dynamic array, no, vector, that's all done internally. So that's sort of the point, or one of the main points, I guess, of a vector is that all that stuff gets taken care of for you. So you don't have to worry about it. Anything else on that subject? I'm kind of thinking if we exhaust everything we want to talk about on chapter 3 / assignment 2, that we could kind of dive into linked lists just a little bit, just to get a little bit of a sneak preview, because I think in the future, like this week, it kind of feels like we don't have that much to talk about. In the future, I think it's going to be the opposite.
There is some talk, I think, on the Discord about
by the way, while you're thinking about that, we're not really, so the vectors have come up a few times in our conversation already. And so I just want to clarify that we're not really, nothing in assignment 2 or 3 is about vectors, right? It's about sets and implementing a set with an array and implementing a set with a linked list. The only place that vector comes into it is just because of this sort of, I'm going to call it workaround for us to be able to, for example, print the contents of the abstract data type. They have a function in there that converts the abstract data type into a vector. But that's as far as vectors come into that, I think. Okay. Okay. So if there are no other suggestions for what to talk about, I might just kind of dive into linked lists a little bit.
I do have one question.
Sure.
Maybe I'm just like missing the big point.
Okay.
But I'm wondering when we're deriving, like I'm looking at array bag and bag interface.
Okay.
I'm just wondering when we derive array bag from bag interface, like, is there anything unique that we're like inheriting there? Like
So, okay. So the question is, when we are inheriting array bag from bag interface, what is it exactly that we're inheriting? Like, why are we even bothering? So basically the only thing that bag interface does is it just specifies for us all of the member functions that we're going to have to create, right? So it's forcing us to implement all of these member functions. That's all it's doing. You know, it's a good technique for making sure that our implementations are consistent, right? So if we have a bag and it's implemented using an array, and then we have a bag and it's implemented using a linked list, but both of those implementations are derived from this bag interface, we know that they're equivalent, they're the same, or at least in terms of functionality, right? Good question. Make sense? Okay. Okay, anything else? Should I pull up? I think what I'm going to do is just pull up my notes on linked lists, because that'll at least give us a picture to start from. And okay. So let's just take a look at this picture for a second. This is a picture of a linked list. And basically the way it works is that we're going to have these things here that we call nodes, N-O-D-E. Fancy word, I guess. Don't let it intimidate you. It's just a word. But each of these nodes is going to have some data, and then it's going to have a pointer to the next node in the linked list. Okay, so these nodes can be anywhere in the memory. Okay, they're going to be in a part of memory that we call the heap, but anywhere in the heap doesn't matter. It could be on opposite ends of the heap, it could be in the middle, wherever. So if we want to traverse the list, to say we wanted to print the linked list out, what we would have to do is just start here with the variable list, which is on the stack, and then follow the pointer. And then, so here's 47, that's the first item. Then go to the next field, which is a pointer to the next node. And then we're here. And then follow the pointer to the next node to get here. Okay. How are you guys with stack and heap pointers? So before we studied pointers, everything was on the stack, right? Local variables are all on the stack. The way the stack works, hopefully if you studied recursion, you might have talked about this a little bit, I don't know, but the way the stack works is that each time a function is called, all of the local variables for that function get allocated in the area of memory called the stack, right? Which is very structured. When that function ends, then it just takes those off the stack. And then whenever we use the new operator, we're storing something in the heap, right? We're allocating some memory on the heap. So list, in this diagram, list would be a local variable in some function, right? But then we would be creating using the new operator to create new nodes over here in the heap. Okay. And then we mark the end of a linked list by making the next pointer in that node equal to null pointer, right? And we represent that in our diagrams just by putting a diagonal through the box. Okay, so let's talk about why we would ever want to use a linked list, right? What's the advantage over an array? Or under what conditions would a linked list be better than an array?
Because you have to load an array, you will have to do that you can just start saving numbers on the fly with a linked list, right? You don't have to define it.
Okay, so you don't have to decide in advance how big to make it. You can just keep adding stuff. Whenever you need to add something, just add it, right? Okay, that's good. What about in terms of efficiency, in terms of runtime efficiency? So okay, shoulder shrugs all around. So here's the deal. Let's say that I need to insert something at position 0 of my array. What am I going to have to do? Just tell me like if you're looking at a picture of the array, not so much code, but like, what am I going to have to do in that array? What am I going to have to manipulate? I'm going to have to shift every item in the array down or over, or however you want to say it, one element, so that I have room now at the front in order to put this new item. That's pretty inefficient, right? We call that a linear function, because the amount of time it takes depends on the number of the number of items in the array. Okay, we'll talk about that sort of thing a lot more later in the course. But if you're pretty decent with your math, you'll know what I mean when I say linear, right? So linear function. So what if I want to insert an item at the beginning of my linked list? Create a new node, make the next pointer from that node point to what was the first item in the list, and then make list point to that new node, right? I wish I could draw that, but I think I probably have a drawing of that somewhere. Right, so this is my insert function, right? So the way I'm going to insert something at the front of the linked list, I'm going to create a new node. I'm going to put the data in. I'm going to make the next pointer point to what used to be the first item in the list. And then I'm going to make list point to that new node. Okay, so like 4 steps, right? No matter how, if there's 10 billion items in my linked list, inserting something at the front takes me like about 4 steps, right? So linked lists are a lot more efficient if you're doing a lot of that sort of thing, right? What are linked lists bad at? You use a little more memory, but still speaking specifically in terms of runtime efficiency. That's you could argue that, yeah. I mean, you could just add another variable that keeps track of that, but that is another step. You can't directly access data. So let's say, for example, that I want to print the last item in my list. how many operations does that take if I'm storing it in an array? Just one, right? I could just say, you know, array size -1 or whatever. Num items -1. Okay. So very efficient, right? What if I want to print the last item in a list that's being implemented using a linked list? Start at the beginning, go one node at a time, all the way down till you get to the end. So now we've got a linear operation, right? So arrays and linked lists have their own strengths. It may depend on the situation, whether you think you're going to be doing, you know, millions of operations where you are inserting at the beginning of the list. You're probably going to want to use a linked list, right? All right, that'll make sense. And this is probably like the fundamental discussion of this class, right? Looking at different implementations, comparing them for efficiency to decide which one you're going to use. Okay, so I'm going to take this code right here. And this is where I wish I had the other computer, but I don't currently have an IDE on my computer. So I'm just using a text editor and the command line. So we'll have to live with that. And it might be kind of small. I don't think there's any way to make it bigger in my text editor. So hopefully this will be big enough for you to see. And I think that's for the, oh yeah, look at that. I've never seen that. Okay, so let me switch over to, actually, I may want to share both of these at the same time. Okay, so this is going to be my client program for the list class that I'm going to start writing here. And the way that I'm going to approach this is I'm going to keep it super, super simple. I'm not going to have it templated. I'm not going to do anything fancy, just the simplest possible thing I can to just as a first introduction to playing around with linked lists. So you can see here, look at this client with me. Hold on, I can make it bigger, right? Is that big enough? Should I make it bigger? Okay. So look at the client and tell me what I'm going to have to implement in my simple list class in order to get this to work. What member functions am I going to need? Insert, print. One more, not as obvious. I'm probably going to need a constructor, right? Because I'm probably going to need my my linked list to start off with the head pointer pointing at null pointer, right? Otherwise, I have no way of knowing whether there are items in my list or not, right? So I'm going to have to use my constructor to initialize that head pointer to null pointer, okay? I'm using the term head pointer, meaning the pointer to the first item in the linked list, okay? First node in the linked list. Okay, so 3 functions. Um, so simple list. Am I recording? No, yes. Okay. Uppercase. Okay, so I'm going to have constructor. Let me make it bigger. What happened to my? Oh. There's my constructor, right? And then I need insert. And that's going to take an int. And I'm going to need print, which is going to have no parameters. By the way, just sort of a side comment, but container classes don't typically have a print function, right? Normally, they provide some way of iterating over every element in the container so that the client programmer can write the print function. Okay, I'm going to cheat a little bit here and just make things simple. We're going to have a function that prints it out just so we can see if we have things right. Okay, and then for private, we just need our head pointer. I think I call it, oh, we need a node too. I think I call it list in the notes. If I had to do it again, I'd probably call it head pointer. But I'm going to stick with what's in the notes for now. So so first I'm going to need a node. This is my, the struct right here that you can't see because it's so small, is, oops, how I define my node. Okay. This is different from how you're going to see it in the textbook. In the textbook, he's going to create a whole separate class called node, right? And he's going to make the data private. So you're going to have to use accessors and mutators in order to get to the data. Okay. So just a different approach. I think it's not a bad thing to see both ways. So then I'm going to have my list data. So just one data member called list, right? And you can see a picture of that here, right? And it's going to be a pointer to a node, right? That's the type of the data member. So, okay. Questions about that? Okay. So let me get my implementation up here now. So let's do our constructor. And what do we have to do in here?
Set the node pointer to both points.
Yep. That make sense? Right. That's our data member that points to the first element. And so this is basically how we represent an empty list, right? So here's the picture of that. Right.
That's the constructor.
Yes.
Oh.
All right. Any questions about the constructor? Okay. So let's insert something. Probably call it something different in my notes. Oh, insert me. Okay. We talked about how we were going to insert something, right? So the first thing we're going to do is create a new node. Okay. Everyone clear on what that's going to do? It's creating a node on the heap. So what? Oh, okay. So right now it looks like this, right? This line of code right here created this part of the picture, right? And then let's put the data in. Someone want to take a shot at how we're going to do that? The actual code. So, are you looking at the lesson?
No, I'm looking at the how you wrote this node structure.
Oh, okay, okay. So so I've got I'm going to be doing something with new node, right? New node is a pointer to a node. So I need to dereference it, right? Let me think back, pointers. And then I want the data part. I want to set the data part of the node to something, right? The data member. So dot data gets new item. Oops. Okay. This isn't quite right, but the concept is right. There's just a little syntactic thing we need to work on. But before I do that, is that clear? Okay. So the problem here is what we want to do is we want to dereference the pointer. So that gives us the node. And then we want to select the data element of the node. Unfortunately, well, I don't know about unfortunately, but it just so happens that the dot operator has a higher precedence in C++ than the star operator does. So what we have here is really this. And that's going to give us a syntax error, right? Because you can't, new node is a pointer. You can't have a dot after a pointer. So one way to fix that would be use parentheses to force it to do the dereferencing first, right? Whoop. Okay, so that would solve the problem. This would work. But it's messy, right? And there's a simplification, there's an operator in C++ that is used to make this syntax simpler. Because this is so very, very common in your code. And sometimes you're even going to want to do this like 3 times in the same line or something. And so, this is probably covered when you studied pointers, but then we don't use it very much in 10B. So anybody know what I'm talking about? Yeah. Yeah, it looks like an arrow. All right. So all of that, and you guys already knew what I was going to say. So we just say, but I think it's important to just show that the first time we talk about it, because that's just a good way of remembering what the arrow is doing, right? Dereference and then select. Okay, so we put our new, we put our data in. So now our picture looks like this. So now we're going to make the, well, let me ask, what do we want to do next?
Should we set the next pointer to our list?
So we want to make this box right here, the next data member of this node, point to the 47, right? The node with the 47 in it. And then what's the other thing we want to do? Point list to the 32. Okay. Does it matter which order we do that in?
Yeah, you want to point next to
47
first. Otherwise, if you set list to, if you set list to the 32 node,
yeah,
then when you go to set next to list, it should be like setting this one.
right, exactly. So if we set, and here's another way of looking at that. If we set the list pointer so that it points at the 32, we have lost our list. We have no way of getting to it, right? So it does matter. We need to do the next pointer first. Right? So pointer, this is pointer assignment. So just review of pointer assignment. Make new node arrow next, point to the same thing that list is pointing to. Okay. And then we need to set list, make list point to the 32, right? Where I'm saying make it point to the 32. Really, I mean, make it point to the node that contains the 32. I'm just saying it shorter, right? So list, make list point to the same thing that new node is pointing at. Okay. So now we have a new list with the new item inserted at the front of the list. Okay, so one of the hardest parts about dealing with linked lists is that there are usually some edge cases that we have to be really careful about catching. So whenever you write anything, any function that's manipulating linked lists, you need to ask yourself, okay, does this work if I'm dealing with the first element in the list? Does this work if I'm dealing with the last element in the list? Does this work if the list is empty? I'm blanking on others, but there's others that we'll come across as we go. And it depends a little bit on the operation, but you just have to ask yourself, what are some possible edge cases, and does my code handle those? So what should we be thinking about in this particular case? No edge cases in this one. So I would want to check my code and make sure that this works if I'm inserting into an empty list, right? Because in my diagram, I took sort of the general case, which is a good place to start, right? And I wrote some code that inserts something at the front of an already existing linked list with a few items in it. Okay, but what if the linked list is empty? Is this going to work? Well, so list is going to be null pointer, right? So list looks like this, right? So I create my new node. Trying to decide whether to bother actually drawing this out or not, but tell me if I think you'll get this. Create my new node. Put the data in. What happens when I say new node arrow next gets list?
next is assigned to null.
Next is assigned to null pointer, which is what we want, right? Because it's the only item in the list now. So it's the last item in the list. And then make list point to the new node. Okay. So anybody want me to draw that? I think it does work in this case. We got lucky kind of, right? Okay. I'll be sure to draw some pictures next week, but let's go ahead and do print, I guess. And so basically you'll notice that what I'm doing here is I am creating the smallest number of member functions that I can and have something to test, right? So I want to get that working, and then I can start adding member functions one at a time, testing everything exhaustively after each member function that I add, right? So that's important strategy, I guess. So print we're going to need a pointer to a node that's going to point to the first element, and then we're going to move it to the second element, and then we're going to move it to the third element, and so on. So node star cur pointer, I guess, and make it point to list, or point to the same thing that list is pointing at, right? And then while cur pointer is not equal to null pointer, because that's how we know when we've reached the end of the list, right? Print the data, and then move cur pointer down to the next item. So in other words, make cur pointer point to what cur pointer arrow next is pointing at. All right. I think I'm gonna just draw a picture here just to make sure we're all good with that. I think okay, so here's how I would draw this. I'm going to say the stack is over here. Heap is over here. And let's say that here's list. This will take me a second to get set up, but once it's set up, it actually turns out to work pretty well. The only hard part is, oh no, I think I have a new version of Excel, so I don't know where to find things. Illustrations, shapes, arrows. Where'd the arrow go? Huh? Oh, there it is. Okay, and then I can make some copies of it. All right, so list is going to point to something over here. Let's say this is a 47. And then let's say there's another node here. And the next field of that node points to that. And let's say in here we have 37. And then let's say over here we have another node. And let's say this is 82. And the next field of this node points to that guy. And then this is null pointer. Okay, so the way my code in my print function is working is I'm declaring a new variable named cur_pointer of type pointer to node, right? So it's over here on the stack. Here's, actually, I guess list shouldn't be in there. It should be over here. And then here's cur_pointer. And I'm saying make cur_pointer point to the same thing that list is pointing at, right? If I can highlight the right thing. So that means cur_pointer is going to be pointing here. Okay, so this is the picture after that first statement on line 15. And then cur_pointer is not null pointer. So I'm going to print cur_pointer arrow data, which causes the 47 to be printed. Yeah, I'm going to pretend this is my output over here. And then I'm going to say cur_pointer gets cur_pointer arrow next. Or in other words, make cur_pointer point to whatever cur_pointer arrow next is pointing at, right? What's cur_pointer arrow next pointing at? The 37. So this means make cur_pointer point to the 37 node. Right? So now back up to the top of my while loop, see out cur_pointer arrow data. So that's going to be the 37. And then cur_pointer gets cur_pointer arrow next, means make cur_pointer point to the thing that cur_pointer arrow next is pointing at, which is this guy, the 82. So that may be a little tricky, but hopefully you'll get the idea. Okay, back to the top of my while loop, see out cur_pointer arrow data, that's going to print the 82. And then cur_pointer gets cur_pointer arrow next is going to make cur_pointer equals a null pointer, right? Because cur_pointer arrow next is null pointer. So this says cur_pointer gets null pointer. So just, right? Now back up to the top of my while loop. Cur_pointer is no longer not equal to null pointer, so I'm done. Okay. Okay. Anything on your minds that we should talk about? Kind of thinking I might just want to call it a day. That was a pretty good start on linked lists.
Yeah, this is pretty helpful.
Okay. Yeah, I mean, you won't even be doing this until assignment 3, right? But yeah. Okay. Trying to think if there's anything else we want to talk about. I think I'm good. I'm going to stop recording. Keep doing that. How do I get, I don't know.